Hello, hi, this is Lakshmikant Tiwari. In this lesson, I am going to start a new video series on data science question and answer. So in each lessons, I'll be taking 5 question and answer of a data science interview, which is most probably the interviewer asked with the candidate. So in very first lesson, I'm going to take a first 5 questions. And the first question is, what is data science, and list the differences between the supervised and unsupervised machine learning. You need to first understand what is a data science. All right. The data science is a blend of various tools, algorithms, and machine learning algorithms, such as machine learning algorithms and deep learning algorithms. The goal of data scientist is to discover hidden patterns into big data or raw data. Now let's see how it is being done. For example, a data scientist have a raw data, and then the data scientist do the exploratory data analysis on this raw data. Then the data scientist try to find out the patterns, okay, and these patterns data scientist try to find out visually, and he just try to understand what is the pattern in this data. And after that, once the data scientist understand the pattern visually or manually, then he try to dig deeper on the pattern. And after that, once the data scientist understand the patterns and the data, then data scientist apply here the machine learning and deep learning. And once machine learning and the deep learning is applied, then the data scientist makes an intelligent decision. In fact, it's not the data scientist, but the model, okay, the model which is being deployed, this makes the decision. All right, and there are various processes involved while selecting this model, like hyperparameter tunings, the model selections, and what type of algorithm data scientists need to select while finally selecting the model. So these are the process of development of machine learning algorithm, and these are the things which a data scientist do. Okay, now let's understand what is the difference between the supervised and unsupervised machine learning. In a supervised machine learning, user have labeled data, but in unsupervised machine learning, user have unlabeled data. And in supervised machine learning, the data can be used as a training data set and then evaluation data set or validation data set, and then user have a testing data set on which user measures its accuracy and F1 score, recall and precision, etc. But in unsupervised machine learning, user directly uses the input data set, input data as a whole. There is no label available to estimate the accuracy, precision, or whatsoever. Okay, and in unsupervised in supervised machine learning, this is used for prediction. Okay, and unsupervised machine learning used for pattern recognition and clustering and dimension reduction. Okay, dimension reduction. And this supervised machine learning, apart from this prediction, the predictions are kind of the classification where it is being used, and then regression as well. Okay, so this is the answer for first question. Let's go ahead and see the second question. The second question is, what is a selection bias? Okay, so the selection bias is a kind of error that occurs when the researcher decides who is going to be studied. Okay, who is going to be studied, and it is usually associated with research where the selection of participants is not random, and it is sometimes referred as selection effect, and it introduced the distortion in statistical analysis, and this distortion, okay, results in the inaccurate study. I mean, the study which data scientist is doing, because of the selection bias, may not be the accurate. For example, if data scientist decides to use a classical machine learning algorithms like decision tree and SVM, then there is a biasness. I mean, the data scientist is manually deciding which algorithm the data scientist is going to select or use. So what are the types of the biasness? Like a sampling bias. A sampling bias, let's say if user wants to, a data scientist select some particular type of the data, and some particular type of the data user, the data scientist do not accept, that becomes the this data biasness. Okay, and for a sampling biasness, it is the systematic error due to a non-random sample of a population, causing some members of populations to be less likely to be included than others, resulting in a biased sample. That means that, let's say, data scientist is selecting some labels are selecting the data from a population, a populated data, and data scientist make some decisions to select some kind of the population more and some kind of population less. There is some biasness. Okay, that's the sampling biasness. A time interval is kind of another biasness, and there is fourth biasness which data scientists make is attrition bias. So these are the four kind of the bias which a data scientist might make, and as a result of this biasness, the study or the results might not be the accurate. Let's go ahead and see the third question, which might be asked by interviewer to any data scientist, and this is very famous. What is bias variance trade-off? You need to first understand what is bias and then what is the variance. Then you might be able to understand what is the bias and the variance trade-off. Bias is an error introduced in your model due to the oversimplification of machine learning algorithms. And if there is a high bias, then there is a very high chance that your model is underfitting. Okay, and at the same time, if your model is overfitting, then there is very high chance that your model might be having high variance. This variance is introduced because of the complexity of the machine learning models. Normally, when you increase the complexity of your model, you see reduction in error due to the low bias in the model. If I draw a bias and the variance trade-off, let me draw this first. Let's say this is the sweet spot, and you get the error kind of like this, and let's say you have here a model complexity, and this axis is representing the error, and then you have here a bias. As the model complexity increases, bias tend to reduce. But if model complexity is low, then variance is low, but bias is high. So how you can draw this? So here we have bias, and this one is variance, and we can introduce this one as a sweet spot. Sweet spot means this is the some area where we have minimum error, and you can say this as a total error. Okay, so what happens in general when you increase the model complexity? Then error reduces, but for a particular only for a particular point. But if you keep continuing increasing your model complexity, your total error goes up. Okay, and here it is going to down. So the data scientist have to make a decision where it has low bias and the low variance, and that point is here. Okay, that means the data scientist has to make a trade-off between bias and the variance. A data scientist has to select a sweet spot where it can find out a minimum of the total error, but it should have some kind of the bias and the variance as well. Okay, so this is the bias and the variance trade-off. You can understand this in a better way by seeing this bullseye, the graphics. We have here low variance, high variance, low bias and high bias. Now you see this point. Okay, in this we have low bias and the low variance, and all the classification is almost nearby the target. But if user have low bias and the high variance, then you see here this is the target, but the final classification, okay, the predicted values are around this one, but it is varying in various directions. And in this way you can say it has low bias, that's mean all the results are almost here, but the variance is high because it is concentrated in all the direction. But if you have a high bias and a low variance, in this case you see here the bias, this is the bias is high, but the variance is low. Okay, the variance is low. In final predicted values, all the values are almost nearby. But if you have a high bias and high variance as well, which comes here in this way, then you see here the bias is high as well as this variance is also high. Okay, so user has to make here some intelligent decision where the data scientist has to make some intelligent decision where it should find a lowest of total error, and of course there will be some bias and the variance. Now let's go ahead and select see the fourth question. Fourth question is, what is a confusion matrix? Okay, a confusion matrix is a table which is number of classes into number of classes. For example, let's say if you have a binary classification, okay, in binary classification you have two classes. In that two classes you will be having 2 cross 2 the table which you can say as a confusion matrix. I'll explain that you later. But if you have, let's say, more number of classes present in your data, then let's say you have n classes. In n classes you will be having n cross n table which will be showing you a confusion matrix. In a confusion matrix you can say, let's say if we talk about for a binary classification for a simplicity, as I said, this is table, okay, and this table is 2 cross 2 table, and in this 2 cross 2 table, you can say this is the actual class, and here we have a predicted class. Okay, in actual class and the predicted class, now let's say if we say this is the positive prediction and this is negative prediction, and this is positive and this is negative prediction. If it matches positive to positive, we say it as a true positive, but if positive, that's the actual class, classified as negative, then we say that this is a false negative. But if actual negative class is classified as a positive class, then we say it false positive. And if actual negative class is classified in actual negative class, then we say it as a true negative. So let's understand it once again. If a positive is classified as a positive, then we say it as a true positive. If positive is classified as a negative, then we say it as a false negative. If negative is classified as a positive, then we say it as a false positive. If negative class is classified as negative, then we say it as a true negative. Okay, so this is a confusion matrix, and this is known as a confusion matrix. And from this confusion matrix, various parameters can be derived, and those parameters are like error rate, accuracy, precision, recall, F1 scores, and much more. And these things can be derived by using these values: true positive, false negative, false positive, and the true negative. Let's understand it in a better way, how we can do that. So here we have the error rate. Okay, the error rate we can classify as this error rate. Error rate can be classified as, let me write it here, as false positive plus false negative. That's mean false positive is this one, false negative is this one. So this one, then plus all the values divided by all the values. So we have false positive, false negative divided by all the positive classes and then all the negative classes. That's mean total number of samples. And at the same time, the accuracy, let's go ahead and see the accuracy in next page. The accuracy can be classified as, here we have accuracy, this is accuracy, the true positive plus true negative divided by total number of classes presents into our data set. And precision, this is precision. Precision can be classified, precision can be calculated as true positive and then divided by true positive plus false positive. And then the recall can be calculated as a true positive divided by true positive plus false negative. And F1 score is harmonic mean of precision and recall. It can be calculated as 2 times of a true positive divided by 2 times of true positive, then false positive and plus false negative. This is how we calculate the parameters which measures the accuracy of the model. Okay, accuracy, precision, recall, or overall you can say the measurement, the performance measurement of a model can be made by using a confusion matrix. All right, let's see fifth and the last question in this video. That question is, what is dimensionality reduction and its benefits? Okay. The dimensionality reduction means reducing the total number of dimensions from a data set. For example, let's say you have a data and which have 300 classes. Okay. If you have a 300 classes, then this is not always guaranteed that you are going to get a better result always. So actually how it happens, let's say you have here number of classes. If you have high number of classes, then it will also results the high number of complexity, or you can say the complexity of a model. Okay, so let's say this axis is representing the complexity of a model and this one is representing as the error. Then what happens, as you increase the complexity of a model, your error starts decreasing, but after some points error starts increasing, as we have seen into bias and variance trade-off. So a data scientist has to make a wise decision, an intelligent decision. So it should select some a sweet spot where error is minimum. Okay, where error is minimum. So what happens, if a data scientist have high number of classes, then that is going to result in high complexity in your model, and that might not be accurate. So the dimensionality reduction is a technique which reduces this dimension to low number of low number of original dimensions. That means less than at least 300. So this could be in result of 2 dimension, 3, 4, or anything to 299 or 1, that can be also included. So what are the techniques which reduces the dimensions? Those techniques are PCA, principal component analysis, linear discriminator analysis, LDA. Otherwise, another one we have a feature selection. Okay, in a feature selections we have 3 types of feature selection methods. The very basic one is a filtering methods, and then we have wrapper methods, and then we have embedded methods. So these are the techniques which reduces the features and which might also increase the accuracy. So what are the benefits? The benefits are simple model, okay, reduction in overfitting, so it reduces the chances of overfitting, and third one is a faster model, and fourth one is lighter model. That's mean if you have low number of classes, it's not actually the classes, this should be features. Okay, so this should be the features, and this also should be feature. Okay, so input features which classify in classes. So it doesn't depends on the classes actually, it depends on the feature. So if you have a low number of features, that's mean your model have will be also faster as well as a lighter. Okay, so this is all about in this lesson. Thank you so much for watching. Please do not forget to like and subscribe this channel. And if you want more videos on the interview questions, please comment below and let me know. I'll make more videos. Thank you. Bye bye.